France.
Thank you. We can say that today parallel file systems are not just scratch, and Lustre as a user home or project directory has become commonplace in areas that are non-traditional HPC field domains. So more and more often, one cluster must support various populations of users, and those users could see each other as a competitor or an indiscrete party. So in order to address this requirement for privacy, we would like to be able to provide encryption for Lustre. And this is what is my talk about today. First, I will explain what we mean by encryption for Lustre. Then I will do a quick recap on my present last year, which was already about encryption and Lustre, but in a different approach. So today, and this is the main part of this presentation, I'd like to present an alternative approach to last year's case study. I will explain what's the current status and what's the remaining work. Okay, so from a user perspective, having encryption means that we want to provide each end user with one or several directories that are spatial in which they could store secret files. So it means those files would be encrypted. From a different perspective, it means that we want to be able to protect data as it is transferred between clients and servers, and also we want to protect data at rest. Last year, I presented a study where I was using encryption on top of Lustre, which means making use of a layered file system that comes on top of the Lustre client mount point. The outcome of this study was that the best compromise appears to be GoCryptFS. So it's a file system written in Go. It's a user space file system, and the advantage is that it's ready to use, it's simple to implement, but the major drawback was its performance penalty. So it was more than 80% performance drop in write sequential bandwidth and more than 70% in read sequential bandwidth. Today, I'd like to present a different approach, which would consist in implementing encryption directly inside the Lustre client. The good news is this is a feature we're going to develop, so we are free to choose the requirements we want to address. Here you have the list of the requirements that we would like to address with this feature. Of course, we'd like to be able to encrypt file content, but also file and directory names. We would like to have a master key from which the actual key used to encrypt each file individually is derived. We would like to be able to support what we call secure deletion, which means when a file is removed, when an encrypted file is removed, its content is no more available in memory on the system. Concerning the way we manipulate the encryption keys, we would like that end users are able to specify which directories they want to encrypt and in which fashion, for instance, with which encryption algorithm. Of course, it would be possible to remove the encryption key from the system so that you prevent further access to the encrypted files. We would like to be able to change the master key that is used to encrypt the files. And last but not least, of course, you may have applications that are accessing files when the application is launched via a batch scheduler. So in this case, there is no end user interactively entering the password for an encryption key, for instance. So we also need, of course, to support this, this access pattern. So how we want to achieve that? As Andreas said, we want to rely on the FSCrypt kernel API, which already exists in the kernel. It's currently used by ext4, F2FS, and UBFS file systems. It's pretty mature from kernel 4.14, which means we can use that with Red Hat 8 or Ubuntu 18. We would like to use the same encryption principles as ext4, which means so the encryption chunk size is the page size on the client. So of course, the size of an encrypted page is the size of a clear text page, which there is no change. Each page, all pages can be encrypted and decrypted independently. And very important, we want all the pages in the page cache to be only clear text data. We don't want to put encrypted data in the system page cache. From a key management perspective, we want to use another tool that already exists. It's called FSCrypt, but it's so it's the same name as the kernel API, but it's a user space tool that is developed by Google. And it's a simple way to decide on the directories you want to encrypt and in which fashion. And we would have to support the encryption policy v2 so that we are able to fulfill all the requirements I mentioned before. And last, ideally, we would be able to share code infrastructure with current work that is going on client-side compression, because we are doing same kind of processing of the data in the pretty much same locations in the code. So we could have a common infrastructure. Here I listed again the requirements, just to mention that not everything can be addressed by Lustre itself. All that has to deal with key managements, deciding on encryption policies, has to be handled by a user space tool. This is not Lustre itself. So that would be, in this case, the FSCrypt command line utility. So what would be the data workflow like? Basically, of course, applications would be able to see clear text data. Data would be encrypted before it is sent to the servers, and then it remains untouched. Conversely, data would be only decrypted upon receipt from the servers, which means untouched before that. So to sum up, it means that servers would only see encrypted data, but would not be aware of this encryption. And of course, only clients may have access to encryption keys. So consider that you have an application that wants to write into a given file at a given offset. So this command hits the Lustre file system on the client. It's converted into a request to a file into a given page. So the client would process to encryption of this page, and then the page is put inside the RPC, and then it is sent normally to the server. The server receives this request, processes it normally. The server is not aware that data is encrypted, so in the end, data is stored encrypted on disk. Now consider that the application wants to read a file at a given offset. So again, the client translates that into a request for a page, and the client sends an RPC to request that page. The server reads the page from the storage backend. It puts it into the RPC. This request happens to be encrypted, but the server is not aware of that. So only the client knows that this page has to be decrypted. It processes to decryption, and then it lets the application access the decrypted content. Of course, because this is a security feature, we need to have a threat model. So you have all the details under LU 12.275. This is just an extract here. First, if we think about offline attacks, so it means when the Lustre file system is not running and you try to access data directly on the servers. Of course, in this case, because we are encrypting file contents and also file and directory names are protected. In fact, depending on the encryption algorithm, we can guarantee confidentiality and also integrity. But what is not protected is file metadata. For instance, we are not hiding the file size or the file permissions or the timestamps or even the extended attributes. All that remains visible, as well as holes in the files. So it means you would still be able to see that your file, even if it's encrypted, you would be able to see if it has holes. Now about online attacks. So it means that the file system, Lustre file system is running, and you try to intercept and get access to clear text data. Of course, we are relying on an existing API and, of course, on existing encryption algorithms. So we are as vulnerable as those algorithms are. Another very important point to understand is that it's not because your files are encrypted that you don't need an access control mechanism. If you are sharing a given Lustre client with other users and you enter your encryption key so that you get access to clear text data, it means that without any access control mechanism, other users would be able to see clear text content. So of course, you still need an access control mechanism, so Unix access rights, ACLs, namespaces, SLNX, whatever, but remember, you still need an access control mechanism. So if the kernel memory on the Lustre client is compromised, then it means that your encryption key, your master key, could be accessed. So it's really important to understand that the master key must be removed from memory as soon as you don't need it to access encrypted files. If the kernel memory on the servers is compromised, then there is no consequence on security for your encrypted files because, again, Lustre servers only see encrypted content and they are not aware of that. And last point, if the specific key that is used to encrypt one file is compromised, it does not compromise the other files, and it does not compromise the master key, because we are using an HKDF SHA-512 algorithm to derive the encryption key from the master key, and this algorithm is non-reversible. So what's the current status? At the moment, I have pushed 5 different patches to LU 12.275. The first one is here to set the global framework that is used for encryption, and it also introduces the dummy encryption mode, which is actually a fixed encryption key mode, which is very convenient for testing purpose. Then there is a patch for encryption on the write path, another patch for decryption on the read path, one for proper file size handling, and the last one at the moment is non-regression tests to exercise this new feature. So proper file size handling is very important for encrypted files. What happens when you have encryption is that consider that you have only 3 bytes in your page. When you encrypt that, it will result in 4K, or let's say page size bytes produced by the encryption algorithm. Then this full page is sent to the servers. So the size as seen by the server is this full page. So the server, the size as known by the server will be the one of the encrypted file and not the clear text file. So we have to carry out from the Lustre client down to the Lustre servers and down to the object on disk. We have to carry out a hint about the actual size of the file in clear text version. Another Lustre subtlety is about checksumming. So I'm talking about the checksums that are computed on RPCs before they are sent on Lustre client and upon receipt on server side. And of course, those checksums must match, otherwise it means that something bad happened on the network between client and servers. Remember that we want pages in the page cache to be only clear text data. So it means that with encryption, the page cache is not what is actually sent to the server. So we must make sure that we are not computing the checksums on pages in the page cache, but on the pages that are actually sent to the servers. Otherwise, there will be a checksum mismatch, and the request will fail. Now let's talk about performance. I run performance test on top of the master branch, on which I applied the 5 patches mentioned earlier. And I'm using the dummy encryption mode. It's AES-256 XTS, so it's pretty serious algorithm. Here you have the description of the test bed. It's a single client performance. I measured bandwidth performance because this is the impact that we expect from encrypting file content, both for sequential and random I/O. First, let's have a look at the bandwidth write performance. So if you look at the 2 blue bars, I wanted to compare the performance of the master branch with the same code plus my patches about encryption, but without actually using encryption. So this shows that when you do not use encryption, there is no performance impact from the code that has been added, let's say, on the normal non-encrypted I/O path, which is good news. Then, if you have a look at the orange bar, it shows the performance when we actually write encrypted files. With 4K IOs, there is not that much performance penalty. The reason is that there is only 1 page to encrypt per RPC, so it happens very quickly. On the opposite, when you increase the IO size, it means that you have more pages to encrypt per RPC. And at the moment in the code, the encryption of pages is done sequentially. So this is one reason why we have a larger performance impact. The other reason is that in order to encrypt pages, we need to allocate new pages. Again, remember, we want the page cache to contain only clear text pages, which means in order to have pages with encrypted content, we need to allocate more pages. So we are spending time allocating pages when we do encryption. On overall, we can see that we have a performance drop around 30% or less in the case of 4K IOs, which is much better than with the GoCryptFS solution, where it was more than 80%. If we have a look at CPU utilization when running this IOR benchmark, if you have a look at the 2 lines, you can see that, of course, CPU usage is increasing. This is no surprise. We are doing encryption, which makes heavy use of CPU on the client side. Then if you look at the bars, we can see that we are spending time in the PTLR PCD threads, which is normal because, remember, we are encrypting pages just before they are sent, they are put into the RPCs to be sent to the servers. So this is actually PTLR PCD thread's job to call the encryption primitives in the kernel. The red bar shows the portion of the time that is actually spent on AES routines, and it's around 8% for a total of 50% of time spent in PTLR PCD. So again, the explanation might be that we have to allocate pages in order to proceed to encryption, and also we are doing encryption sequentially. Now, if we have a look at read performance, again, the 2 blue bars are completely similar, which means we are not introducing any regression in the regular IO path. If you have a look at the orange bar, you can see that there is a 20% performance drop in sequential read, which is again much better than with the GoCryptFS solution. If we have a look at CPU utilization, again, CPU usage increases by 20%, which is normal. Here, PTLR-PCD thread time spent by PTLR-PCD threads is up from 15 to 20%, and AES time spent AES routines is around 8%. So we are, let's say, much more efficient here, and that can be a clue that that's because of time spent in page allocation. Here with read, we do not need bounce pages. We just decrypt pages in place. So we are actually more efficient, and we spend more time decrypting content. A quick look at random I/O performance. So random 4K I/O. Here you have the write performance. You can see the bars are completely similar, and it's the same in read. In fact, the thing is that with random I/O, Lustre has other performance bottlenecks, like request aggregation, locking to manage. And so we could say that having encryption when your workflow is essentially random, then would not have any visible impact. So the remaining developments, of course, we will have to develop everything around encryption of file and directory names, and also links, and then run metadata benchmarks, because of course this would have impact. Also, we will have to develop code for the ability to set encryption policies on directories, and so let end users decide on which directories they want to encrypt and how. And we will also have to work on a number of optimizations. So here I'm just listing one, which is about the encryption context. So the encryption context is stored by FSCrypt kernel API inside an extended attribute, and it basically says how a file is supposed to be encrypted. The thing is that handling extended attributes in Lustre adds additional requests to read and write this extended attribute. So we would need to, for instance, be able to set this extended attribute while the file is created, so that we do not have an additional set XRTTR request. And similarly, we would need to be able to read this encryption context as we have an open or lookup request, and save a get XRTTR request. We will also have to face a number of challenges that have to deal with the other Lustre features. For instance, with DNE, we don't know if there will be an impact regarding file name encryption. We may also have an impact, for instance, with data on MDT. We must make sure that data, the part of the files that are written on MDTs, is actually encrypted. And with FLR or file migration or even request replay, we must make sure that we are not encrypting file content twice. And as a general purpose, the performance penalty should only be the result of the time spent on encryption and decryption, and not other known behaviors. So as a conclusion, I think you can say that this first step is quite encouraging. We are able to have a good level of performance, even if it's POC quality code. And that would be a good replacement for the GoCryptFS solution. Of course, at the cost of this current development, but then it would be easier to implement. And of course, as an opening remark, the next hot topic would be key management. That is to say, where to store master keys that are used to actually encrypt and decrypt directories on Lustre. And that's all. Any questions?
So how are you going to, what's the plan for encrypting the file names then? Because they're obviously aren't going to the page cache.
What do you mean exactly?
Well, so you're going to need some completely different mechanism for encrypting file names, right? I mean, what's the idea for file names?
So in the case of file names, of course, it will not work based on a page size. So it's simply buffers that are located to store the encrypted result. So I said that for file content, we are using the page size as the chunk size, the granularity at which we proceed to encryption. But it's possible to decrease this granularity down to 16 bytes, which means that, for instance, for a file that has one character in its name, the encrypted version of that would be 16 bytes long. But it's just a buffer that would be allocated. And this is not something that we are handling ourselves. This is some primitives that are provided by the FSCrypt kernel API.
So how does it look on the, if a non-encrypted client looks at this file name, what the file name looks like?
It's like scrambled. You have, of course, it's only printable characters, so that it doesn't break an ls command. So as I said, the file name and file content is hidden. So if you don't have the master key, it's like scrambled. But you can still see the permissions on the file, the timestamps, and so forth. So you could still go down the tree and try to have a look, but there will not be any valuable information except sizes, permissions, that kind of stuff. So it does, of course, this is a solution that does not hide a directory structure on Lustre.
Other questions?
Yes, I have one. If we were to use HSM with this encryption, would the file in the HSM backend be in clear text? Since
That's
it's
a good
client?
question. I haven't thought about from an HSM perspective. So yeah, that's one more challenge to address. Thank you.
I have another question, please. How about performance on the server side? I mean, you mentioned just the performance of the client side during the encryption. Is the encryption performance on the server side the same like a client side, or how would like the picture?
So I will talk about that and present that on Developer Day. The idea is to, in the same request, the same write request that the client sends, there is one additional information that gives information about to the server about how many bytes in the page are actually real data as seen from the clear text version of the file.
I think there's a misunderstanding there. The servers are not going to do any decryption of the file data, right? It's encrypted on the client, and it's sent over the network, and then it's stored directly by the servers. So the servers don't do anything with the data, right? So if you are the administrator and you have access to the servers, you still can't decrypt the files, right? It's only the users with their encryption key on the clients that can decrypt the data. Yeah.
You would like to have encryption over the network. So if the client is sending data to the server, it should
Yeah, so there's already, I mean, Lustre already has network level encryption, right? Kerberos and shared secret key, right? That uses AES encryption over the network, and then the server side decrypts the data and writes it in plain text, right? So that exists today. This is a different feature that encrypts on the client and it stores the data encrypted on disk. Yeah, it's over the network encrypted as well because it's encrypted on the client. So it's end-to-end encryption and it's stored encrypted as well.
Ah, okay, so the data then is saved, encrypted on the server in that case.
Yeah, so there's no overhead on the server at all.
Here in the goals that I'm mentioning, it's an end. We are protecting data as it is transferred from the clients to the servers and also data at rest. You cannot have only protection with this feature. You cannot only have protection of data on the wire. As Andreas said, this is more a shared key or Kerberos feature that is already available with Lustre if you want that only.
Okay, thank you.
So, hi. So you talked earlier about the handling a situation where there is a batch scheduler doing stuff on behalf of a user. How do you imagine this to work in the new approach?
So the key to address this requirement is to be able to support multiple master keys. So in fact, instead of having one master key, we would, it's like sharing. Consider that you have one directory that is shared among different users. You do not want to share one encryption key between different users. Each end user would have its own encryption key, but the master key would be encrypted by those keys, and you would provide the end users with something that actually decrypts the master key. So it enables you to still have one master key because this is how FSCrypt works, but then the way to access this master key can be via different encryption keys on top. So in the case of a batch scheduler, it means that the batch scheduler would have its own key in order to unlock the master key, just as any other user that is part of this group allowed to access the directory. That would be the way to address this requirement.
Okay, thanks.
Last question.
So with such encryption, the client with key only can read and write to some file, but client without key can still break the data, writing anything wrong.
Yeah, absolutely. There is no protection. The only thing you can have is, depending on the encryption algorithm that you pick, you can have a way to protect the integrity of the file. So it means that you would be able to detect if something that you describe, such as you described, happened. But it doesn't prevent in any way.
Some additional mechanism.
Yeah.
Thank you, Sébastien.
Welcome. Thank you.